So I'll give you an overview of what the field of machine learning is. My goal really is to have you really understand the fundamental concept, how things work at the highest level possible, and to give you some links and resources so that you can then go to the more hands-on part and get started in more technical aspects. Because I think that understanding what it's really about, how things work, what the deeper, higher level concepts are is really what matters. Learning how to code things, that's something that you can find online, that you can find lots of workshops on. So really, what is machine learning? So let's get started with a few definitions. First, there is the very, very large, all-encompassing field of artificial intelligence. And artificial intelligence is really any field where some computer, some machine, some human-made system is trying to mimic a form of biological intelligence. So it's a very large field. It encompasses really very many disciplines. Machine learning is a subfield of AI, and really what it focuses on is the training of algorithms. That means having algorithms that by themselves, without being encoded through precise recipe, will learn to perform tasks better and better. And over time, with experience, which means data, the performance is going to improve. Now, you might have heard of deep learning, and deep learning really is just a form of machine learning that involves a type of algorithm that is called a neural network that is sufficiently deep, meaning sufficiently complex and large. So deep learning, just think of it as some complex neural networks that get better at performing tasks with experience, meaning repetition over data. But I'll go over the way neural networks work in a bit. And then because you're in the humanities, what you might be the most interested about is what is called natural language processing. And this is really a subfield of AI that is focused on human languages. And it's going to be based on machine learning techniques, but particularly applied to text. So why has machine learning become so very popular suddenly? It's not something we were hearing much about when I grew up, and now it's really everywhere. Well, in fact, it's really not a new concept. It's something that was suggested in the 50s and 60s, but we just didn't have enough resource for it and enough computer power and data for it at the time. But the concept has been there for a long time, and it's very powerful because it allows to do things that other forms of computing just cannot permit. In typical computing, like any other form of programming beside machine learning, you have a programmer that writes code in a certain language, be it Python, C, R, whatever. And a program is really a set of instructions. So you write some code, and that code just tells the machine to do a number of tasks. And programs can be extremely powerful, they can be extremely complex, but they have to be explicitly written by a programmer. So let's look, for example, at the task of identifying whether a dog is in an image. For a human, that's a fairly simple task. We intuitively know how to identify a dog in an image, even if it's a cartoon, a drawing, one breed of dog or another breed of dog. We have this dog concept, and we can apply it to images that look incredibly different from one another. Now, if we wanted to create a program in the typical classic programming way to do this task, we would have to do some kind of if-else loop that would be insanely complex to tell the computer, okay, if these pixels look like this, it's a dog. If not, it's not a dog. If the pixels look like this, it's a dog. Otherwise, it's not a dog. But it's not possible to go about with this approach, because the number of possible ways a dog can be represented in an image is so immense that there just isn't enough computing power in the world for this to be possible. So machine learning takes an entirely different approach. Instead of going with this explicit programming instruction approach, you have what's called a neural network, which is an algorithm, and I'll go into the detail of that a bit later. And you pass through it a ton of data, a ton of, in this case, images, some with dogs, some without dogs, and you tell the algorithm at each image, dog, not dog, dog, not dog. And if you do this long enough, eventually your algorithm is able to identify whether a dog is in an image or not on images it's never seen before. And if you think of how, as humans, we learn to identify whether or not a dog is in a picture, well, I mean, that's kind of what we do. As we grow up, as very young children, we learn through this repetition, through this learning process, this is a dog, this is not a dog. So really, the way algorithms are trained
Marie, I'm afraid I've accidentally muted you.
Okay.
There, good. Thank you.
Can people hear me now? Have I been muted
Yes.
for a while?
No, just for about 3 sentences.
Oh, okay. Okay. So I was saying, this is very much the way as humans we learn whether or not something is a dog, and machine learning is really deeply inspired by the way biological organisms learn, which is very different from the classic programming approach. But because it involves tremendous amount of data and a huge amount of computing power, when Arthur Samuel, who's the American from MIT who first came up with those ideas in the 40s and then the 50s, came up with all these concepts, there was a lot of excitement that died out pretty rapidly, because at that time there just wasn't the computing power to do that. And if you think again as how we humans learn how to identify whether something represents a dog or not, we do it in this approach, but we have this huge amount of computing power, which is the brain. So now we have a lot more computing power. Of course, it's nowhere as big as what, say, a human brain is, but it's getting bigger and bigger. The advent of GPUs and the vast amount of data available have really revived the interest in this Samuel approach, and that's why we've seen this explosion in the interest of machine learning. But so how does it all work? Okay, yeah, you throw data at an algorithm and it learns, but how? So it really depends on the type of learning. The first type of learning, and that's the one I will explore with you in detail, is called supervised learning. And you've actually learned about supervised learning, except you didn't think about it in the context of machine learning in your schooling already. When you think of a regression or classification, those are forms of supervised learning. If you have a number of dots in a graph and you try to apply some function through those points to then be able to predict future values based on some variable, well, this is a form of machine learning, except it's very basic. So the overarching goal of supervised learning is to find a relationship between some inputs and some outputs. And with, again, the example of whether or not a dog is in an image, this is a type of supervised learning, because the input are going to be the images, a bunch of images with or without dogs, and the output is going to be is there a dog or is there not a dog? So that's a type of supervised learning that actually is classification. You classify dog, not dog, based on some input. There is other forms of learning, and I won't go into that today, but one is unsupervised learning. And that's when you don't have pairs of input-output, so you don't have a pairs of X's and Y's, you just have some X's. You just have some data that are unlabeled. So that means that they don't have their Y variables. So this is, for instance, what you do when you look at PCAs or clustering or social network analysis or market segmentation. Basically, you have a bunch of data, and the goal here is to try to find some structure within the data. And then there is reinforcement learning. And in that case, instead of having some input data and then some labels, like some Y's, dog, not dog, you instead give some reward or punishment to some exploration that the system is doing. And this is what happens, for instance, when algorithms learn to play some games. You can train an algorithm to play Super Mario. The algorithm is going to move Mario in a system, and Mario can fight, jump, walk, do a bunch of things, and the penalty would be death. The reward would be some bonus point. So you have some form of feedback based on the actions that the algorithm is taking in a certain context. And over time, the algorithm accumulates some experience and becomes better and better at performing the appropriate action in a particular context. But let's look in detail at supervised learning, because this is really where Arthur Samuel's theory in the 50s, like this is the context in which he really formulated his theory, and this is really, I think, the birth of machine learning. So it's very interesting to understand how it works. When you want to go about building a system, an algorithm, a model that will learn through machine learning, first you have to decide on an architecture. An architecture is just a bunch of code that sets some parameters of your model. For a neural network, the architecture will decide how many neurons, like artificial neurons, you have. So you have some kind of programming structure in place. That's called the architecture, and this doesn't change. But then you also have some parameters, and the parameters are some initial values in your system. And you can start them at random, or in the case of transfer learning, you can start with parameters that have already been trained in a similar system and that have some better values. But in either case, you have some starting parameters that aren't very good. Like your architecture and parameters at first are somewhat naive, totally naive if your parameters were chosen at random, or less naive, but still not very performant if you have taken them from pre-trained models, as in transfer learning. So you have this structure and it hasn't learned yet. So then you need a lot of data. And by a lot of data, we mean a lot of labeled data. So that means a lot of inputs, outputs pair, or inputs, labels pair. If we think of this example of whether or not there is a dog in an image, well, your inputs are going to be all of the images, with or without dog, and the labels are going to be, in this case, just two, dog, not dog. Okay, so you have all these labeled data, and you pass them, well, first you have to do things properly, you have to split them into two sets. A set that will be to train your model, and a set that will be to test your model. You will put maybe 80% of your data in the train set and 20% in your test set. Then you only use the train set to train your model. So you take the train inputs, and along with the parameters that you've set at random or you got from some other model, you pass that through your architecture. So you run this through the architecture and you get some predictions. So you pass some X's through the architecture along with some parameters and you get some Y's. But because you have labeled data, you know what labels, like the true labels for your inputs. So if you pass a bunch of images, you know actually which ones have dog, which ones don't. So then you can compare your predictions, what your naive model has said about dog or no dog, and you compare with what you have to see, okay, was it correct? Was it not correct? And with that, you get some value that's called the train loss. And there are various ways to calculate the train loss. There are various techniques, but it doesn't matter how it's calculated. The idea is that the train loss is some value of accuracy, like how good were those predictions. And the lower the train loss value, the better your model is. So you have some train loss. At first, it's going to be very bad because your model is quite naive. But with this train loss, you tweak your parameters a little bit. In technical terms, this is a process called back propagation. But really, the idea is that based on how good or bad your predictions are, you're going to tweak the parameters a little bit. You're going to adjust them. And those parameters, they're nothing magical. They're just a bunch of numbers in your system. And so you're going to move some numbers up a little bit. You're going to move some numbers down a little bit. And then this parameter and architecture, that's your future model. You're going to do this very many times. The reason we need a lot of computing power to do machine learning is that first we need a lot of data. So at each iteration, at each loop, there's a ton of inputs that has passed through. So there's a lot of calculation that happens at each iteration, but it takes very many iterations. No, that's actually something different. I will talk about model bias later on. The train loss is not a form of bias. It's just a measure of performance of your model. Bias is different, and that's a very important concept, and I will talk about it. Yeah, thanks for the question. So at each iteration, the train loss will decrease a little bit, but it takes very many iterations to get good parameters. So that's why you need a ton of computing power. So once you are satisfied with your result, once your train loss is good enough, then your architecture that hasn't changed, that you set at the beginning, you decided, okay, I want my model to be this many neurons, this type of architecture, this type of model, this like this size and this and that, and your initial parameters that have been tweaked at each iteration until they become very good parameters. So that architecture and your final parameters, that becomes actually a program, that becomes your model. And once you have the model, you can test it. So here you can pass your test inputs that the model has never seen. So you can pass some very new images, the 20% that you had put aside, images the model has never seen, so not images it's been trained on, and you get some predictions, you compare them with the test labels, and then you get the test loss. And the test loss is how performant your final model is. So there are ways to save models. You can save them and pass them on, because when you save a final model, you save the full model. So that means that you save both the architecture and the parameters. So this architecture and parameters, that becomes really a program that you can save. You can save it to a file and pass it on to someone. And that model then becomes just like any program. You can then use it the way you use any program. When you have a typical program, you send inputs to a program and you get some outputs. So the way we create the model is very different. Instead of having a human, a programmer, write every single element of the program, the way it's done in traditional programming, there is this training process that is automated following this insight of Samuel that auto-adjusts through an automated process the parameters. But in the end, you just end up having a model that you can use like any other model. So once you have your model, for instance, about dog identification, then you can just put it in the world out there and people can use it. And you can put some pictures to this model and you get whether there is a dog or not in the picture. Yes, I can use the mouse. Why? Oh, instead of using my arms. Yeah, okay, yeah, that makes sense. Right.
Oh, yeah, I think that's what indeed. They meant, yeah.
Yeah. No, that would be more useful indeed. Thank you. So I've mentioned many times, okay, artificial neural networks, but what are they? So really, again, this whole idea of machine learning was very deeply inspired by biological systems. The analogies, of course, are fairly limited, but there's been a lot of inspiration, and I think we can draw a number of parallels. So in biological networks, like in our brain, you have action potentials between neurons, and you have these deep networks of neurons. Well, I don't think that it is true that for humans it takes just a few, because we can, as adults, learn with just a few examples because we have built these abstractions, but we did grow up learning a lot. So transfer learning is when you take a pre-trained model and you take your pre-trained parameters and apply them to a new system. Humans do transfer learning all the time. So yes, once we've learned by living for many years, we have this abstraction and we can learn very quickly to identify anything. But if you take a newborn, I'm not sure they would instantly identify whether something is a dog or isn't a dog. So we have built all this initial training in a way, while your program at first is very naive. So a biological neurons has some directionality to it. You have some dendrites that get some signals and pass them along an axon and then sends them to another neuron. An artificial neuron has really a similar system. All these things are just numbers, really. You have some inputs. Your inputs are numbers. You have some weights, which are also numbers. Then you have some function here, which makes some very simple operation, just such as a weighted sum, for instance. So it's really very simple arithmetics that is at play inside an artificial neuron. And then your weighted sum is passed to an activation function, and you have an output, which is also a number. So in the biological system, you have a bunch of electric signals. In an artificial neurons, you have a bunch of numbers, but the schematic, theoretical function is similar. So then you put them inside networks. So the brain is insanely complex. You have all these incredibly complex connections, and that is something that really is very limiting for artificial systems. We are building systems that are more and more complex and have more and more fancy architectures, but of course we will probably never match the complexity of biological systems, because brains are so incredibly complex in their connectivities. The first neural networks had just like a bunch of layers. Each little dot represents an artificial neuron. So these little systems that does a bunch of very basic arithmetic and then pass them through a function. So all these little very basic arithmetics are performed at each of these little neurons and then pass on the number to the next layer and etc. So lots of very simple operations, but very many of them, which is where GPUs shine because GPUs aren't very smart. They can do only very basic computing tasks, but they can do them in vastly parallelized fashion. And so they can do very, very many basic operations at the same time, which is exactly what we want for neural networks. So machine learning really makes a perfect use of GPUs. And then there is this function at the end of each neuron, and that's an activation function. There's a bunch of functions that have been used. It's just a way to get some output from our weighted sum, and it's kind of equivalent to some threshold in biological systems, some electrical threshold. So there are quite a bit of analogies. Of course, in biological systems, the process of learning is the strengthening of some connections between neurons, some neurons that die, some neurons that get associated with other neurons. In artificial systems, the process of learning really is this tweaking of parameters. So as I said earlier, at each iteration, the parameters get a little bit better. And so the learning process just resides in these numerical values of the parameters. Thanks to this iteration trying to minimize some loss function, so the some value of performance of your model. So the very first neural network that Samuel came up with was a fully connected neural network, and it had just one hidden layer. So you have these little artificial neurons, you have the input layer, the output layer, and in the middle you have what's called the hidden layers. And if you have more than one hidden layer, that's what's called a deep neural network, and that's when we talk about deep learning. So deep learning is just a neural network that has more than one hidden layer. That's really it. So the very first system was incredibly basic and thus incredibly limiting. Samuel showed that in theory, you could solve anything with such a basic system. But in reality, even though, yes, this could in theory learn anything, it's so basic and limited that you would need an infinite amount of time for it to learn a lot of things. So it's not practical. But we have developed increasingly complex networks by, of course, it pales compared to the complexity of the kind of connections you have in the brain, but by making things a little bit more complex. For instance, when you have images, images are a bunch of pixels on a two-dimensional plan, and the data is spatially structured. For instance, if you have some sky in the picture, well, there's going to be a lot of blue pixels next to each other because the sky is going to be all at the top. So you have all these correlations, spatial correlations in the data, and it's kind of a loss not to make use of it. There's a lot of pixels in an image, so there's a lot of data, but thanks to these spatially correlation, like these special correlations and this spatial structuring, a type of network was developed that's called convolutional neural network. And it makes use of this by reducing the amount of data between layers. So it does what's called pooling to just from a bunch of pixels, so a bunch of data points, extract a single point. So that can be done by calculating some average or taking the maximum value, or there's a lot of techniques, but the goal is to make use of the structure in the data to simplify the model and have fewer data points. Now, if we think of text, each word is also a data point, and but they're not random. As in a picture, in pictures, pixels are not just random values put around. They have some structure. Well, in text, it's the same. You don't have random series of words. There is a structure. Here, the structure is not spatial, it's temporal. So some words often come before other words, for instance. So there is a different type of network that was developed that's called recurrent. And this one tries to make use of this temporality by looping over time. And then in recent years, there's been some really cool stuff happening. And the way, for instance, translation algorithms or captioning algorithm, so you pass an image to an algorithm and it automatically generates a caption. The way they've been built is by combining two of those RNN. So one is called the encoder, and one is called the decoder. And by combining two RNNs, you can do some kind of translation or captioning work, but it's incredibly slow. And one problem with RNNs is that because of this looping pattern, you cannot run things in parallel. So you cannot make good use of GPUs. So it's very, very slow. But in 2014, there was this really revolutionary paper that came about that talked about the concept of attention. In machine learning, the concept of attention, the idea is to give added weight to important words. In speech, some words have a lot of meaning and others don't. And then this has been applied to images as well. In an image, some areas of pixels have a lot of meaning and others don't. And this is really how the biological brain works. So here again, there's a lot of inspiration from how we function, which is very different from the classic approach to programming. As humans, when we are presented with an image, we don't analyze every single pixel with the same amount of attention. Our evolutionary history has conditioned us to subconsciously, instantly focus on the characters in the picture, for instance, or certain elements in the picture. Otherwise, the amount of brain power we would have to use to function if we were paying the same amount of attention to every single thing in our environment would be overwhelming. So through evolution, our brain has learned to focus on some signals that are much more relevant to our biological fitness than others. So this is really that concept applied to machine learning. Giving more weight, again, in a neural network, the weights are just some numbers. If you give more weight, you give larger numbers to the weight on some neurons. So by giving added weight to important things in images, in text, etc., you can train models much, much faster. And then the second revolutionary paper came about in 2017. That was the creation of a new model called the transformer. And remember that RNNs use this recurrence. So the transformer, that paper suggested that using only this concept of attention, just this attention mechanism, was without the recurrence of RNN, was actually achieving better results. And the huge advantage of removing the recurrence is that now you can parallelize the work. You can run this at high speed on GPUs. And so this new model, the transformer, that is based on the concept of attention, is what has given rise to, for instance, Burle from Google, that you might have heard, and something you've definitely heard, GPT-3 from OpenAI. The T in GPT means transformer. So GPT is a generative pre-trained transformer. So ChatGPT is a transformer. And now there is a GPT-4 already, and things are getting better and better. But so just realize that in the field of the humanities, in anything that has to do with text, in translation, text recognition, human language understanding, there's been insane progress done thanks to this concept of attention and then the advent of transformer. So this is a very exciting time to be in the field of text and to work with anything that has to do with human language, thanks to those new models, the transformers. Now, someone earlier wrote something about bias, and yes, that's really something that's very important to keep in mind. There are a ton of limitations to these models. The first limitation is data bias. If you train any model on biased data, of course, you're going to get a biased model. And I mean, data is always biased to a certain extent. And this is why, I mean, you have all heard of sexist or racist algorithms. And why? Well, that's because there is a ton of data out there that was created by humans and that is sexist or biased in all sorts of ways or racist or whatever. And when you use that data that's out there to train a new model, well, your model is going to have the same bias as the data it was trained on. So the important thing is to keep that in mind. And when you use some data to train a model, it's very important to document the limitations and the scope of your data. Because one very common pitfall is called out-of-domain data, is that you take some data that was applied to a certain set of circumstances, you use it to train a model, and then you apply your model to a different application that is out of the scope of your initial data. And that can lead to a ton of problems. You can have domain shift. That's when the model becomes totally inadapted to a certain condition it's trying to solve. And then maybe the problem you might be the most familiar with is the feedback loop. You have an initial bias, and because of this process of training, you exacerbate the problem. A classic example is, for instance, in some neighborhoods, there is more police because of some initial, for instance, racial bias. And because there's a lot more police, well, there are more arrests. And so because we believe that there are more arrests, we need to increase the amount of police. So if you take a data set that has the amount of arrests in each neighborhood in a city, and you use that data to train a model to make a plan on where you want to dispatch your policemen, if your initial data is biased, well, you're going to get a model that is extremely biased, and that can have real world implications, because then you're going to dispatch your policemen in a biased fashion, thinking that you're doing the right thing. So the solution to all this is to ensure that there's a human circuit breaker in the system. Your model, of course, doesn't have any insight. Your model is trained through automatic repetition. You feed it data and it becomes very good at doing some predictions. So it's a very performant tool, but it doesn't have some higher level insight or control. Only humans can do that. And so it's very important to have humans in the system that can give some thought as to What kind of data was fed to the model? What is the goal we are trying to achieve? Are there problems with the model we're having and its usage? Then another pitfall or limitation of these systems is that algorithms are not supposed to transform us, and sometimes they actually do transform us. YouTube recommendation algorithms, for instance, actually transform the subject. So you are supposed to train a model to an application, but you're not supposed to actually transform the subject in the process. And then there can be just plain bugs with real-life consequences. There have been some well-documented problems already where just a bug in the code written in an algorithm led to some problems. So machine learning is very powerful. It's really a huge, a tool with huge potential, but it has limitations. So now, okay, I've talked a lot about what machine learning is in the highest possible level, but what if you want to actually use it in your research, or what if you want to start exploring how it could be used for your own everyday work? So let's talk a little bit about tools. In the field of NLP, so natural language processing, there are very many options, and here are maybe the most popular options. There are others, of course, but this is really a list of the ones that are most commonly used, and those are links, and you have access to the slide. The slides are on a website that is there to stay, so you can use it as a reference, and so you can click on any of these links and explore tools. A lot of these tools are Python libraries, so it might be wise to learn Python if you're interested in machine learning. Although, I mean, if you're keen to learn Julia, the Julia programming language also has a lot of really amazing machine learning libraries available. But many libraries work on C and Python, and Python is a lot easier to learn than C. So if you're brand new to programming, learning Python and then learning one of these tools would be a really excellent starting place. Now, which one should you choose? The list I gave here are the most popular tools. There are many others that are also excellent, but I made sure not to put in this list proprietary tools. And of course, you are free to do anything you want, anything you feel you should. And if people around you, if your supervisor, if your colleagues, if the literature you read involve some proprietary software, and if that's what you want to learn, of course you can go ahead. But my one really strong recommendations would be to stay very clear of those. And an example of proprietary software, for instance, would be MATLAB. The reason I feel so strongly about the value of open source tools is manifold. Universities always pay for licenses for those proprietary software. So you have them available to you for free as a grad student. And you might think, oh my God, there is this fancy, expensive tool that is available to me. I should really take advantage of this opportunity and make use of it. But I personally believe very strongly that this is a trap. Companies really have a lot of marketing approaches towards universities and get students into their tools through this trap. And the downsides are that you will learn the tool, you will become expert at a tool, but as soon as you graduate, you won't have access to this tool anymore because those tools are incredibly expensive. So if you are hired by a company that doesn't pay for the tool, all of your expertise will be for a tool you can't use anymore. You will, for instance, have written the analysis of your thesis in a tool in some file formats that you won't even be able to open anymore once you graduated. So you'll be locked in and won't even be able to look back at your analysis. Proprietary tools are often black boxes because the code is not open. You can't go explore it. The company knows what the code is doing, but nobody else can go have a look at what's going on in that code. And then something else that I think is really very important is that some universities in other countries don't have the money to pay for those very expensive tools. And a lot of researchers out there that are not associated with big universities, or a lot of NGOs, a lot of companies don't have access to these tools that are very expensive. And so if you write some interesting paper with some method using those proprietary tools, these methods will not be open, will not be, those people who don't have access to these tools will not be able to reproduce your method. So for an open and equitable research, I think it is very important to use open tools. But beyond all of this, honestly, the open source tools have actually become a lot better than those expensive tools. And the reason is that when you have an open source tool, you have a huge community of people using the tool and asking for particular functionality in the tool, and or contributing code to the tool, making it better, creating all sorts of edge cases that are very prevalent and interesting in research, or they are discovering and fixing bugs. So when you have a huge community using a tool versus a much smaller pool of programmers developing a tool in a company, just because of the numbers, open source tools actually have become much more performant. So choose whichever tool fits best your community, your supervisor, your colleagues, the literature, and the type of task you want to perform. But open source tools, I think, is the way to go. So to finish, I'm leaving you with quite a bit of resources that you might want to explore. These 4 videos that are on YouTube are, I think, absolutely phenomenal to learn about neural networks. Grant Sanderson has this 3 blue, 1 brown YouTube channel, and he puts together incredibly pedagogical videos on all sorts of things. There are some that are excellent also on linear algebra that might really help you if that's something that you've always hated and you forgot all about, and you suddenly might need to understand a little bit of what's at the nitty-gritty, at the mathematical level of machine learning. And if my overview was too vague, too high level, too theoretical, and you're like, well, I'm still living not understanding at all what a neural network is, watch those. They're phenomenal. In about an hour, you're going to know so much about neural networks. So I highly, highly recommend you watch those. I found them so useful. Then the literature, when it comes to machine learning, is very open, very big, and Archive is this open access preprint catalog, and it's very, very active when it comes to machine learning. But so much so that it might be overwhelming to look for Archive. Yeah, the website is there to stay, so I can post on the Slack again. Yeah. You can, these slides are just online. They're built into a website that I developed for teaching. So you can browse it anytime. And you can follow those links at your own leisure later on. So it can be overwhelming to search the machine learning literature, but Andrzej Karpathy wrote an Archive variant that he called Archive Sanity that makes it easier to search the Archive literature. And those links all take you to a lot of machine learning literature search tools. So if you want to read papers, those are very good starting place. Then this is a blog post that I think could be interesting. It's on the MIT website, and it's advice for machine learning research students. So what do you mean by qui choisit l'algorithme? Or maybe that's for the French course though. So yeah, it was written in French, so I guess that's for the concurrent French session. And then there is this website called Stack Overflow, and Stack Overflow, you might have encountered it if you do any kind of coding, is a question and answer site that is incredibly helpful and has a lot of answers on anything that has to do with programming. It's a community Q&A site, and it works with tags, and there are lots of tags that are very relevant for the topics of machine learning. Now, because machine learning, if you want to train your own model, needs a lot of data, it's very useful to have open data sets to train your data. Because data is everywhere, data is all around us. But when we say we need a lot of data, what we mean is we need a lot of labeled data. And while data is everywhere, labeled data is kind of the gold people need to train things. And so these sites give lists of open data sets. And so if you need open data sets, you can search through those. Then one machine learning Python library or set of libraries that has really become incredibly popular in academia and in research, and that is absolutely amazing, is PyTorch. And so here are some links to PyTorch, and that's the machine learning library that I personally use. So I find it absolutely amazing. And then, because a lot of these libraries run on Python, here are some resources on Python. Your first step, if you want to get into machine learning, might be to use Python so that you can then learn one of those Python libraries that are specific to machine learning. So that's that for my presentation. I will post the link of these slides again in the chat. And if you look at the website that you might be very familiar with by now, I can post it again in the chat as well. You can navigate to my presentation this way. If you go to the program in English and then introduction to machine learning, there is a link here for all of the material. This will take you to the website in which I build a lot of material. And for instance, if you want to start learning Python, I also have some workshops and material on Python that you are very welcome to browse if it is of any help to you. And the slides are here. So if you click here, that will take you to the slides. So it's all linked to the HSS website, so you can keep browsing it. And this website is there to stay. Those links will remain, so you can access it just whenever in the future. Now, we still have about 15 minutes, and I would love for anyone who has a question to just unmute themselves and ask away. You can type in Slack if you'd rather, or if you don't have a microphone, but we can open a conversation and you can ask about anything you'd like, or ask for clarification or advice or whatever.
Well, I have no doubt that people are bowled over by the amount of information you've shown us, Marie-Hélène. This is a fascinating field, and it's one in which if any of you are new to all of this, don't be afraid to ask newbie questions, and don't think you're alone, because last year, this time, I was in your position. We've got a raised hand from Paul. Paul, go ahead and unmute yourself if you like. if you're
I had a slightly related question about Julia. I was curious if it's mature enough to use also for machine learning.
Absolutely. Yes, yes. There are many very good tools for Julia, actually. So if you already know Julia, yes, you can totally, where do I have them? You can totally dig into the options. There are very many options, depending on what you want to do. The most fancy option, the best, is the successor of Flux. So I think it's called Lux. Okay, because there was the first machine learning Julia package I learned was Flux, but now there is I'm not sure whether it's a clone or something a bit different, but something based on Flux that is even more performant, that allows you to explicitly set every single parameter. I just don't remember what it's called, but Flux is really extremely powerful to build neural networks. If you want something a little bit more out of the box, a little bit easier to get started, there is CNET that will have some frameworks already set in place. Like Flux gives you all of the tools to build your neural networks. Flux would be for Julia the equivalent of PyTorch for Python. In PyTorch, you have all of the tools to build neural networks. So you can do absolutely anything you want from there, but you have to encode everything yourself, basically. So Flux is the same. It's incredibly powerful, but you have to build the networks. There are packages that make it easier to get started. So there's scikit-learn that's an implementation of the classic scikit-learn that people use in Python. But there's also CNET and other things that allow you to use some higher level layers to not start from all the building blocks. But yes, there's a lot of tools, and yeah, some of them are definitely fairly mature. Absolutely, yeah.
Marie, I see a few more questions have popped up in Slack. Johan says, given the high resource requirements machine learning imposes, would it not be advantageous to focus on the C programming language rather than interpreted script languages like Python?
Well, I mean, if you know C, if you've already learned C, sure, I mean, why not? But if you're new to programming, Python is way easier to learn. And while Python is very slow, while C is very fast, all these machine learning libraries, they are actually built in C or C++, and they can be accessed through Python. So if you know C, I mean, why not? But if not, my advice really is to learn Python and to take advantage of the fact that Python does run C libraries written in C in very efficient ways. For instance, you might have heard of NumPy, which is a Python library that allows to do computations on arrays very efficiently. NumPy is written in C. PyTorch is written in C++. So unless you already know C, I think it is an easier route to go through Python, and I don't think there are actually downsides to it at this point, because those libraries are really well optimized and written in C.
Okay, and Barus, or maybe B.A. Russ, asks, what does linear algebra have to do with this? Are we solving systems of linear equations, adding weights to internal parameters, and are the tensors two-dimensional? In that case, are we just multiplying matrices? Oh, that's
exactly.
mathematics.
Arrays, exactly. Yeah, exactly. That's exactly that. Except arrays are like matrices have 2 dimensions. Arrays have any number of dimensions, and you are doing linear algebras on arrays because there are more than 2 dimensions. If you look, for instance, at this example I've taken all along about identifying whether or not a dog is in an image. So first, your image has 2 dimensions because the data are pixel values in a 2-dimensional object. But then you have actually a third layer, because if your image is in color, you have an R, a J, and a B channel for the colors. So you already have 3 sets of data, 3 sets of value of number for each pixel that represent its latitude, longitude, if you want, like its X and Y coordinate on the image, and then its RGB value. But then you need to use batches of images to train. So each batch is a collection of images. So that's a 4th layer of data, if you want. So yeah, so you have what are called tensors. Tensors are these arrays of numerical values that are the data that you pass to your neural network. And so libraries such as Flux in Julia or PyTorch in Python, they're just very good at they have a data type that is a tensor that can handle all of those multidimensional arrays with all of the values that you need to train your model. And they pass all those values through your architecture with the parameters. So the parameters are just a bunch of numbers that are also stored in some arrays, and do some very basic calculations like weighted sum or pass through some activation function, and you get some outputs. So outputs are also a bunch of values that are also in an array. And so if you look at those videos, it will explain everything in a tremendous amount of detail, but that's exactly what's going on. You have basic calculations being performed on arrays of data, and then the process of backpropagation is performed based on the loss values that you have that were obtained comparing your predictions with the true values, like the labels of your trained data set. And through backpropagation, you tweak every single value of your tensor, so your array of parameters, through automatic gradient descent, to keep it very simple. That's automatically performed by the computer. You could do it all by hand, but that would be a tremendous amount of insane calculation. But these libraries do all of this automatically. And so yes, if you watch those videos, it will all make perfect sense. So those videos are so very good. I felt they do a much better job than I could ever do to explain the mechanisms. So I wanted to give a much higher level explanation, and then leave you with those videos to get into the an entry into the mathematical aspect of it. So I hope I answered a little bit.
I think you've taken an incredibly complicated topic and expressed it reasonably clearly. I take it from that question that there's it's the computing power that you have that allows you to get so much further with the data than you would do if you were just doing all the math yourself. I mean, it would take years to do the kind of calculations that these programs and packages can perform. We have 5 minutes left, and I wanted to make sure we have a couple of more questions here. Rachel asked in the chat, Marie, can you speak a little more about how parameters are adjusted during the training phase for creating a model? So she understands conceptually, but I don't understand what kind of adjustments would yield different results and why.
Yeah, and that's in the back propagation process. And again, this video does wonder at explaining it. Watch in order because they all build from each other. So before jumping into it, watch the other two. But really, Grant does an insanely beautiful job at explaining it with lots of beautiful animations. So watch these, and in an hour's time, you will have understood it. I promise you, it's beautiful.
Okay, and then there was one last one. Pierre asked, have you heard of people using PHP instead of Python or R?
I mean, you can use anything you want based on your prior knowledge and what colleagues and people around you are using. For instance, Stanford is a very, very dynamic machine learning university, and their NLP team developed the core NLP library, and it's written in Java. So a lot of tools are written in Python because Python has become by now, and by a long shot, and it's been like that for years, the most popular language out there. So because Python is so popular, everybody does things in Python, so there's a lot of libraries for Python. But yes, you could do machine learning in any programming language that has any computational abilities. So if you don't want to work in Python, there are certainly other approach, and NLP is in Java. So once again, any tool in any language, I think, is great if it matches your need. I would just be very cautious around proprietary tools. So I would keep an eye on how open the tool is before investing a lot of time learning it. But other than that, yeah, sure, there's a lot of approaches. And look in the literature for what tools people use. And really, if you're just getting started, well, PyTorch, I think, is the incredibly powerful, and it's really popular in research, and it's amazing. If you're just getting started, jumping into PyTorch might be a bit of a difficult strategy. Learning the basics of Python and then exploring NLTK, for instance, might be an easier approach because it's a platform that will have a lot of NLP specific tools built into it. You won't have to write complex neural networks from scratch. There's a lot of functions that will allow you to tokenize your text, meaning transforming your human text into tokens, into numerical outputs, because of course your network cannot process pixels or text. It can only process those text. I forgot I have to click like this. There is a fairly new library that's called PyTorch NLP. It's about 1 year old, so it's very new. It has those NLP specific tools built from PyTorch. So if you're interested in PyTorch, you might want to explore this, but I have no personal experience with it, so I don't know. It has quite a few stars on GitHub, and it's open source, and it's built on PyTorch, so it looks very promising, but I haven't tested it. But that's something that might be worth looking into as well.
Oh, that is so marvelous, Marie-Hélène. And we are at time now. So I have posted in the chat here the Zoom link for the next session in case people don't have it and they'd like to copy it. It starts at 2:30. And I just want to encourage everyone, if even if even if this doesn't entirely, if you're not at the level of this yet, you will get there. And there are many workshops that the Alliance provides. So between this weekend and going forward, keep an eye out for workshops that will help you get the basics of Python and that sort of thing, and become accustomed to grabbing a few libraries, and you'd be amazed at how quickly you learn this stuff. So thanks very much, everybody, for attending.